Okay, we will go ahead and finish up with the Arrhenius expressions, where they're coming from, some energy diagrams, that kind of fun stuff, as far as Chapter 13 in Kinetics go. So far we talked about concentration, nature of the reactant, and mechanisms. We haven't really addressed temperatures or catalysts necessarily yet. Okay? Catalysts will really end with the whole discussion. Before we push a little bit further in, let's take a closer thought process look at temperature. Okay, so what we're going to do is do a game where we actually push to the absolute extremes. So a lot of the types of problems that you can expect me to at least think about and ask and try and put onto exams are these kind of thoughts. Okay? If we take a look at an individual reaction, for it to occur, we have to have the reactants interact with each other. Okay, so we pick an individual reaction of, say, A reacting with B. Okay, so if we have this A plus B goes to our products. Okay, for this to occur, A must interact with B, and they must somehow bump into each other. Okay, well, is temperature going to play a role in that? Okay, so what we're going to do is push to the extremes of temperature. What happens if we drop the temperature to 0? Okay. Temperature is kind of this weird, vague thing we measured as heat or energy. Ultimately, we see a lot of that energy in motion. So if we've got something moving, it has some energy. And it would, in theory, have some temperature associated with it. So if we drop to 0 degrees Kelvin, absolute 0, we would expect no motion. Okay? Well, if we freeze the particles A and B in solution, and A never touches B, could we get a reaction? No, they never interact. Okay? What happens is we increase the temperature. Now A and B start to move a little bit more, so maybe we get an interaction. Okay? Let's increase it a lot more. Now A and B are moving a lot more, which means the likelihood that we're going to get interactions between two particles actually impacting each other dramatically increases. So as we increase the temperature, we would expect that the rate for our reaction should also increase. Okay? Just kind of as an overall picture. Doesn't always work, but that's a nice rough estimate as to what's occurring with this. Okay? Well, Arrhenius came along and kind of took this same kind of concept. So he's going to combine the idea of how temperature and the concept of kind of the beach balls hitting each other comes together into some mathematical expression. Okay? So when we looked at our beach balls, we looked at the number of interactions and the type of interactions. Okay? So if we changed our beach balls, and I talked about putting Velcro, so we put partnering Velcros on one section of the beach ball. If we look at how those beach balls bounce around, some of the times where there's not Velcro, the balls will bounce off of each other because there's nothing to hold them. So what we're looking at is an elastic collision. They bounce away from each other. If, however, we then spin those balls and they happen to impact and collide where the Velcros align, now the Velcro holds tight, and those two beach balls now become one larger beach ball, if you will. So what we've got is an inelastic collision. Okay? And Arrhenius kind of looked at it in this respect as well. Said that as we run an individual reaction, there's different types of collisions that we could get. We could get one that produces products and one that doesn't. Okay? So what we're going to do is look at our elastic and inelastic collisions according to these kind of things. An elastic would be non-product forming, and our inelastic would be product forming. Okay? So he went through and did this kind of collision model of how a reaction occurs. Okay? And if we look at the number of inelastic collisions with a beach ball, we get an infinite amount. Okay? Because no part of that is going to interact differently. Okay? If we, however, change to a molecule, say in this case, I can't quickly identify what that molecule is fast enough, so we'll just say it's a molecule. Would we expect the same types of collisions? Okay. No, it's a different shape. Okay, and for this matter, we even have different colors. We have different atoms. So we get different possible inelastic collisions. This is also going to control the different types of inelastic and elastic collisions. Okay, so what he tried to go through and do was come up with some kind of expression that could kind of control all of these things. Okay, and the things that he took into consideration were the orientation of the individual molecules. So if we went back to the beach balls with the Velcro, only a particular orientation where the Velcro is actually aligned do we get product. Then we could also look at energy, which is ultimately our temperature. Only if those beach balls are actually moving around, do they have the correct energy, could we possibly get these collisions to work. Okay? Excuse me. So with all of these things kind of jammed together, he kind of tried to interpret these as best he could. Okay? So the orientation versus temperature. So which one's more important? That's a bit kind of a rough decision to kind of make, because if we don't have enough energy, we never get a reaction. But if we never have the proper orientation, we never get a reaction. Okay? So those aren't going to be the easiest to work with. Which one's easier to monitor, though? For orientation, we're looking at atoms and molecules. We can't see or feel or grab any one of those. We could look at solutions, but we could never see an individual orientation. Or back then, we couldn't see an individual orientation of the molecule. Temperature, however, we can measure just by really roughly our bodies. We can say, oh, it's hot out versus it's cold out. Okay? We then invented ways to monitor that approximate feeling with thermometers. So we do have a way of measuring our temperature. Okay? So Arrhenius, and I'm not sure where to classify him as a physicist, mathematician, or chemist, but a group of these guys got together and were able to find a relationship between the rate of our reaction and temperature. Okay? And they were able to predict certain possible things and kind of nettled out of all of these possible ideas this equation, okay, or one form of this equation. The K, actually I think I got it on the next page. The K in that is your rate constant, okay? And that directly gives us information about the rate. And remember, if we looked at our rate expression every single time was rate equals K times concentration of some number of reactants. So for an individual reaction, the concentrations could change, but we still always get that one-to-one relationship between the rate and the rate constant. Okay? So if we have a bigger rate constant, what does that mean about our rate? We get a faster rate. Okay? So what they were able to determine is that our rate constant has some dependence on these other terms. Okay? So first thing that's important here is the activation energy. Okay? This activation energy is an intrinsic property to an individual reaction, which means as long as the reaction stays that particular reaction, it will always have that activation energy, regardless of what other things change around it. Okay? The other thing that they introduced is they happened to notice that the gas constant. Why do you think the gas constant might show up? Well, remember way back at the very beginning, we said what phases were we going to primarily work with? We said gases and solutions, which ultimately, to a first approximation, were the same thing. It's just what was the dissolving substance. In a solution, it's something like water, okay, a liquid state. If it's a gas, it's the air around, so it's just the gas state. It's what is our reaction actually occurring in. Okay, the gas relationship, they did lots of studies with that. You got Charles' law, Boyle's law, all those ideal gas relationships. So the gas constant does play a huge role in understanding it. That's at its most simple and basic form. We don't have to worry about surface area interactions or things like that. Okay. One thing to watch out, though, with this gas constant is we're no longer using the one we're used to from the gas law chapter. Okay. And that's because we're now converting our gas constant to include units of energy. And energy is monitored using joules. okay, as our standard form. So what we could go through and do, if you really wanted to test it, is use the gas constant you're used to, which is 0.082, and convert those units into joules. And that's where you'll end up finding that you will end up with this number, the 8.314 joules per mole times kelvins. Okay. The last thing that's kind of confusing in here is this A term. I didn't include it. T. Let's do T first. T stands for that capital T. You'll notice is different from our lowercase t that we used before. Capital T is going to refer to temperature. Okay. And what I would ask you to go through and do here is substitute a couple temperatures in. Okay. We won't worry about activation energy or R, so what you can go through and do is say, okay, K equals e to the negative 1 over t. Pick a couple different temperatures and see how the rate constant changes as you change your temperature. And what you should notice is as you increase the temperature, you get a larger temperature value, you get a larger rate constant. So we do end up still seeing that same relationship. It just happens to not be linear in this respect. Okay? Unfortunately, we don't always get what we want, nice direct relationships. Okay? The last term here, or really I guess the first term in the equation, is A, our frequency factor. This very, very roughly equates to the number of successful collisions. Okay? So that means as we run the reaction, we get all of these interactions, our molecules bounce into each other. Only a certain number of those actually produce products. That certain number can be converted into roughly a percentage value. That's your A value, okay? Roughly, okay? It's a very tricky term. It's not easy to really quantify without getting into some probably hardcore quantum physics. So we aren't going to worry too much about it, except that you should be able to calculate it and know what it means, okay? For an individual reaction at an individual temperature, it's going to stay constant. Okay, so it's never going to change on you. We know it's a constant. It's just ultimately a correction factor to make sure this relationship holds. Okay? So Arrhenius was able to determine all of this. I know this is a lot of mathematics in here, and what we're going to do at the end of this is kind of say, okay, what do these things show? And we'll see that in a little bit. But first, let's kind of get into it. So first off, our equation isn't easy to see a straight line for. If we tried to plot that, we're not going to see a straight line. What we're going to get is a big curved exponential line. And way back in Arrhenius' day, remember, we don't like curved lines. Things need to be as straight as possible. Okay? So what they ended up doing was manipulating those numbers a little bit, and they were able to find that they could change the format of the equation into something else. Okay? And that's what's shown in the red box. We've got the derivation above it. The red box is ultimately what you want. What is special about that expression? Okay? Well, what we have here is actually y equals mx plus b. We have the equation of a straight line. So we can go through and kind of highlight these things. We get the ln of a being our y-intercept. Our y value is the natural log of our rate constant. And I didn't draw this very neatly, but our x value is 1 over t, so let me erase that a little bit. Okay, and the slope of our line ends up being our activation energy divided by r, or negative of the activation energy divided by r. Okay, so this is helpful because now we can plot our data, temperature and rate constant, to determine the activation energy for an individual reaction. And that activation energy is what's necessary to clear the reaction, to allow the reaction to occur. Without that activation energy, we don't make our products. Okay? And we'll see that pictorially in a little bit. Okay? So what we've got is that equation, equation of a straight line. Okay? you will end up having to solve a variety of questions along these lines. Again, just like we did with time-dependent solvings, what we want to do is see what the question's providing us as far as information goes. If you see anything about energy or temperature, you're going to be moving into the Arrhenius expression. The Arrhenius expression is the only one that shows a relationship between the energy and the temperature. Okay? So if you see those terms kind of float up in your question, you should immediately be thinking of this section, and there's ultimately three questions that you could, or three equations you could be using. This one that we've just seen here, and the one previous, the exponential version. Okay? What does this ultimately mean? Okay, well, if we look at kind of a physical representation of what's occurring in our reaction, okay, what we're trying to do is push that rock from over this hill, okay, get it over to the other side. So really what we've got is our reactants, which is R, moving towards our products, which we've got represented as P here. And to be able to get that rock over there is going to require a certain amount of energy. Okay? That energy, if we were looking at the rock, is going to be relative to how big of a hill we're going to have to push that rock over. Okay? If we now zoom in on an individual reaction, what we're going to start doing is now, instead of looking at it as moving it from point A to point B, we'll look at it as a reaction coordinate. Okay? Meaning, as we shift from left to right, we're shifting from reactant to product. The other thing that we're going to add to this is an energy axis. So the energy is going to be on our y-axis. The higher up we go, the higher in energy we are. Okay? So that hill is going to require energy to get over. Okay? Oh no, this isn't showing it the way I want it to. In earlier chapters, in 151, what you looked at, it's really not showing the way I want it to. What you looked at was how you got from position A to position B, or our reactants to products. We didn't care about anything above, we just cared about the energy of position A and position B. So you just looked at the difference between those two. That's ultimately thermodynamics. Okay? And in 151, you made the simple approximation that that energy is roughly equivalent to your enthalpy, or delta H. When we look at thermodynamics in 151, we're going to add a couple extra terms to that, because it's not officially just delta H, but it's pretty close. Okay? What we're trying to look at in this chapter is kinetics. So kinetics doesn't care necessarily about the energies of our reactants and products, but how much energy it takes to get to the point where we can become products. So if we're going to be that ball, I have to provide enough energy to move it stepwise up this hill to get to this very top. Once I'm at that very top, if I take an incremental step further to the right, I can now let gravity pull it downwards. Reactions are doing ultimately the same kind of thing. Once we're at the point where we're at that high energy, we can now kind of cascade down into our products and expel that energy in some other form. Okay? Either as heat in the case of an exothermic reaction, or potentially light or other forms. Okay? So other things that we can add to this, really irritated this picture didn't work. The activation energy is the energy necessary to get from our starting point to that point where now we don't have to push it anymore. Okay? So that difference between those 2 points in energy is our activation energy. And that's what's going to prevent our reaction from occurring. Okay? So to get over that barrier, we have to supply energy into our reaction. How do we supply that energy? Because in a reaction, we can't just push it or pull it. What we're going to do is typically supply it in the form of heat or temperature. Okay? So what Arrhenius was able to do was to first off be able to determine our activation energy, which gave us an idea on how much temperature it would require to actually clear the activation barrier and allow the reaction to progress forwards. Okay? One of the other things that he kind of addressed at this point is that peak now gets called something else. We get it refer to it as the transition state, okay? Or the point at which we transition from being reactants to products. Okay? And it's only at that point. To either side of that point, we're either a reactant or a product. Okay? I would ask that you download the file and get rid of that stupid rock pushing person in the middle so that you can actually see what's actually happening underneath. Because I think the figure is going to be a bit helpful here. Yeah. So your textbook takes Arrhenius a little bit further. Actually, not quite. These are some of the more approximations that I want you to be able to think about and reason your way through. So what happens to the activation energy if we increase the temperature? Okay. Well, temperature's not going to change the height of the hill. It changes how much energy we put behind the rock. So what would happen is we change the temperature. We get the rock over faster, but does that change the energy or the activation energy? No. The activation energy is intrinsic to an individual reaction, meaning it doesn't change. So what's our result? Nothing. Activation energy is a physical feature of the reaction. It does not change for that particular mechanism. Okay? What happens to the rate constant if we change the temperature or we increase the temperature? Well, if we increase the temperature, we clear that barrier easier. Okay, so if we put up Hercules and push that rock, he'd probably push a lot easier than any one of us could, and the rock would get over to the product side a lot faster. Well, if it gets across faster, the rate goes up. If the rate goes up, that necessarily means the rate constant likely changed as well. Okay? So as we evaluate this, we could think about it just as we did there, or we could go back to the Arrhenius expression and we could try and do those substitutions that we talked about earlier. Okay? So take a few guesses at different substitutions with the temperature there and see what it becomes. Okay? So as K increases, or K increases as our temperature increases. Okay. What happens to the rate of the reaction? Well, we ultimately just solve that. If our rate constant goes up, then our rate must also go up. Okay? And that comes back to our rate expression that we've been working with so far. Okay? The book takes this Arrhenius expression even further and then allows you to compare multiple different reactions and conditions. When you see these types of problems, it's ultimately just a plug and shove. All you're going to do is plug in numbers and just solve through it. So if you see two temperatures and two rate constants, this is the equation you're going to be using. Okay, so this is the third equation from the Arrhenius chapter that I said you'd need to watch out for. Okay, this equation will show up in your equation sheet. It's not one that I'm a particular fan of, because really all it is just plug in numbers and chug away at it. There isn't really any mathematics or algebra involved too much in it. Okay, which means probably won't show up on the exam. At most, you could expect to see one question on it. Okay. Last thing that we could do is take a look at catalysts, which is going to bring back our energy diagrams. Okay, so our catalyst is going to end up speeding the reaction, and it speeds the reaction by changing the mechanism by which the reaction occurs. Okay, so if we go through and calculated out a big rate expression, got all the orders of everything, we're happy with it, and then we added a catalyst to the reaction, we'd have to go through and recalculate all the orders, the rate constants, everything, because the catalyst ultimately changes how the reaction actually works. Okay. So, pictorially, what's happening? If we took a look at the reaction of x plus y going to z. Okay? So what we're saying is our reactant was x and y, so we take x plus y goes to z. As the reaction occurs, as the reaction occurs on its own, in this case, the picture shows, we have one transition, okay? Which means this reaction occurs in one step. We take x, we add it to y, and immediately we form z. Okay, we're our product. There are no intermediates. There aren't any individual steps involved with it. One step. So one hump, one step. Okay. What happens when we add the catalyst? Actually, before we add the catalyst, the thing that's going to determine how fast this reaction occurs, like we said, where kinetics exists, kinetics is the energy difference between our reactant and our transition state, or the height of our peak. That is going to determine how fast our reaction occurs. So without the catalyst, we get that large hump. Okay? So when we add a catalyst, it's going to change the reaction. And in the process of doing that, it's going to speed it up. So to speed it up, the activation energy must drop. Okay? So when we go through and take a look at the catalyzed reaction, you'll notice that the activation energy is much lower. Okay? So now what we want to do is say, well, how did this change the reaction? Well, how many humps do we have in this case? Okay, well, we've got one here, one here, one here, and one here. So we are going from x and y to z, but we ended up forming different products along the way. Okay? Those products, we had a product 1 here, product 2 here, product 3, and then we ended at z, which was our final product. Okay? Those products, because we never actually isolated them, or one of them, according to our equation, we come up with a better name for it. What's that better name? Begins with an I. We're looking at an intermediate. So when we add the catalyst, what we've got is 1, 2, 3, 4 steps, because we've got those 4 humps or activation energy barriers, and we have 3 intermediate products. Those intermediates continue to react and propagate forwards to make your final product. Okay? So we know the mechanism has changed because we see a varying number of steps. Okay? So that's how our catalysts end up functioning. Okay? Some catalyst terms that might end up showing up, you'll see homogeneous, heterogeneous, enzymes, lock and key, all this kind of fun stuff. Your textbook goes through and discusses it. I'm not all that concerned that you know about these, but they're there. Okay? Homogeneous just means the reaction's occurring all in one phase. Heterogeneous means that you're looking in different phases. Okay? So your catalyst may be a solid and your reaction's occurring in solution, so different phase. Okay? Enzymes are probably where you'll most likely see most of your catalyzed or your catalyst reactions, because I noticed a lot of you are interested in the biological fields. Okay? So that's where you're going to see biological catalysts. There's different theories behind enzyme catalysts. The primary theory that most people are aware of is kind of the lock and key model, which works fairly well. You get an active site somewhere in the enzyme where the chemistry occurs. So your materials come into the active site, the enzyme does some stuff and spits out the product. Okay. The substrates would be what reactants are floating around that need to react with your enzyme. Okay. So those are just some terms that might show up. Okay. I do want you to read through this chapter or section of the chapter. There's not going to be a whole lot of questions on the exam from it. 1 to 2 seem reasonable to me as far as catalyst terms. Okay. Before we do that, part of that catalyst chapter comes back to these kind of energy diagrams. I'm a big fan of the energy diagrams, particularly of the one that doesn't show up well in this case. Whoops, come on, where is it? Oh, it's all the way back here. Particularly of this energy diagram. If you get rid of the rocks, that energy diagram is going to show up again and again and again this semester, okay? Because it's really, really important to understanding the overall picture of why we're doing this. Okay? All of the mathematics that are being pounded and thrown at you, in my opinion, blame the physicists, blame the mathematicians. The chemists came through and said, these are the pictures. Those mathematics, the numbers generate these pictures. The pictures allow us to understand what's happening. The curves that we see, the height of those peaks, all comes from the mathematics, and so you have to be able to manipulate the mathematics to get through it, but that's not ultimately what you need to get out of the class. What you need to be able to do is to interpret, understand what's happening with the equations, and kind of do quick manipulations. At least that's what I would hope you would get out of it. The mathematics, guaranteed if I talk to you 6 weeks after this semester ends, I don't think a single one of you will be able to do any of the questions that we've talked about. Okay? So hopefully that gets you in a slightly better mood after looking at all this mathematics. You'll be able to get through the homework, I believe, now fairly well on your own. If you've got questions, come into class on Monday with a list, and we'll go through, spend 30, 45 minutes if necessary, work on some problems, make sure you're getting kind of comfortable with the material. Okay? Please be prepared and expect to start chapter 14 on Monday. We won't go into it too much, but we'll definitely talk about it at least a little bit. Okay? I will get those lecture slides for chapter 14 posted, and I will post the new slides for chapter 13. Okay, so if you've probably already seen, some of the slides have already changed. So go back to Canvas, re-download those slides, and you should be good. Okay. The last thing that I just want to point out that you've got access to, way back when we were talking about how to solve with all the algebra and rates and all that fun stuff, I had a mean instructor question. I've got the solution at the end of the slideshows, so I'll step through it real quickly here. You can pause it at any point that you want to, pause the video, so that you can see what's happening at each step when we go through to solve this problem. This one's a little bit more difficult than some of the other problems that you've seen, because if we take a look at the concentrations for NO, we don't have an experiment where the NO concentration stays constant. Okay? So I will now attempt to be quiet and just slowly tap through this. Just realized I don't think I directly talked about this part of it. 1 to the nth power, doesn't matter what n is. Okay. Put in n equals to any number you want, you're still going to get 1, which is one of the reasons why it cancels out. Okay, see you Monday.